All right, so let's do this one. We're going to draw the shear force and bending moment diagram for this problem. I'm going to start by finding my reactions at A and C. It may be, like I said, it may be a little bit hard to see, but this connection here at A is just like a smooth connection. So all we really have there is a vertical reaction. There is not going to be an X reaction or a moment. Now at C, again, that's hard to see, but that's just a pin. So again, we'll have just an X and Y reaction. I should be able to find those pretty easily from this system. And to make it easier for me there, I'm going to go ahead and resolve this distributed force to a concentrated force that's equivalent. So the area under that curve, let's see, it's 3 kilonewtons per meter. It's 4 meters. So this will be 12 kilonewtons at about 2 meters up from A. So now with that as kind of my free body diagram, I'm going to solve for those reactions. First, I'll sum moments about C. Make sure my structure is in equilibrium. When I sum moments about C, Cx and Cy, they don't create any moment. This 24 kilonewton and this 12 kilonewton force both create what kind of moment about C using the right-hand rule? They're both positive. So the first one would be the force is 24 kilonewtons times 3 meters. Then the 12 would be 12 kilonewtons is the force, and the distance is 2 meters. And then I have my reaction at AY. What kind of moment does that create? Should be negative. So the force is AY, and the distance here would be 6 meters. So what is AY? 4, 6, 18, 22? What do you guys get? I may have done that too quickly. 20. I get 22 in my head. What do you guys get? Anybody playing along at home?
I got 16.
You got what?
16.
16 is the answer? I did something wrong in my head.
I got 14.
You got 14? I'm getting, 12 and 4, 16. I don't know why I got 18. And it's positive. All right, so now we can sum forces in the y direction. I've got AY acting up. I've got CY acting up. And 24 is down, so that's negative. So if you put AY in here, you can solve for CY. It looks like it's going to be, 8? That seem reasonable? I think you guys have checked out on me. Have you checked out on me? No response to that either. Excellent! So what do we have? If we sum forces in the x direction, we have what? Cx is to the right. And we have 12 also to the right. So it looks like Cx is going to be minus 12 kilonewtons. Did I lose anything along the way? Looks reasonable. Now, in this particular problem, I only have one common point, B. So you can find the reactions at B, the internal forces at B, using either AB or BC. And I don't know, I don't see much difference in either one. I'll just do AB. It comes first alphabetically. So if I look at a section from A to B and draw that free body diagram, this is what I'm going to get. I'm going to get AY, which I just solved for, 16 kilonewtons. I've already resolved my force and found that it was equivalent of 12 kilonewtons. Oops, at 2 meters and 2 meters. And now at B, I'll make assumptions for the directions. I'll say I've got a force in the X direction, a force in the Y direction, and then a moment. And again, I just make assumptions for that. So let's find those values. I think the best place to start, the easiest place to start, is to sum moments at B. So we'll do that. So you can see Bx and By, they really pass through B. They don't create any moments. So all I have there is the moment By, which with my sign convention is positive. And then what else do we have creating moment about B? We've got this 12 kilonewton force. What kind of moment would it create? Positive. And then I've got this force down here. Is it creating any moment? No. So I just have the 12 kilonewton force with a moment arm of 2 meters. So it looks like my moment at B is going to be negative 24 kilonewton meters. I'll go ahead and sum forces in the Y direction. And when I do that, I have By, it's acting up. I got 16 kilonewtons, it's also up. That's positive. I don't think I have anything else. So therefore, By would be negative 16 kilonewtons. Same magnitude, just opposite direction. So you can see that this section AB is going to be in what? Tension or compression? Compression. Now we also want to keep hold of By because even though it's an axial force in AB, it's going to be a shear force in BC. So that's important. And then the last bit of information we need here would be the X force. So we'll sum forces in the X direction, assuming right is positive. So I have Bx to the right, positive. And I have 12 kilonewtons to the right, positive. I got nothing down here, so it looks like Bx is negative 12 kilonewtons. So I got everything I need. So now it's time to draw the shear force and bending moment diagram. So we'll start with section AB. So I'm going to take this and I'm going to kind of rotate it over. And we'll draw it right here. So here's the... Now, do I have a force in the X direction at A? No, because it was... So there's no shear at A. Is there a force in the X direction or shear force at B? Yeah, it was 12, right? And it was negative. So that means it's really up on AB, right? So if I come over here, I should now see a force up at B of 12 kilonewtons. No shear at A. There's my shear at B. Is there a moment at A? No. But there was a moment at B. What was it? We got negative 24. So I assumed it was to the right here. So it's going to be not to the right. It's going to be this way. And don't forget that I had an applied force along the edge, and that had a value of 3 kilonewtons per meter. So there's the loading on the section from A to B. So I can extend a couple lines to create a template. I can come here, establish positive X, positive shear. All my units will be in kilonewtons. Let's see what we've got. So what's the shear starting here at A? 0. What's the shear over here at B? It's 12. Is that positive or negative? That is negative. Now remember, our differential and integral relationships say the change in shear between any 2 points is the area under the load curve. So the change in shear from A to B should be the area under the load curve from A to B, which is, it's rectangular, so base 4 meters times height 12 kilonewtons per meter is negative 12. And if you start at 0 and you subtract 12, you get negative 12, so that matches. The slope of that diagram, or the slope of the shear diagram, should be equal to the loading. And what's the loading everywhere from A to B? It's constant, so it's 3, and it's negative, so I get a negative slope. So it's dropping 3 for every one we go. So there's that's our shear diagram. So let's look at our moment diagram. We're almost out of time. So there's positive X, positive moment. All of our moment values will be kilonewton meter. What is the moment starting here at A? 0. What is the bending moment at B? There it is. It's negative. It's 24 kilonewton meters. Is that positive or negative bending moment? Negative. And we know that the change in moment between any 2 points is the area under the shear diagram. So what's the area under this shear diagram? What's a rectangle? 1/2 base, 4 meters, times height 12. That's negative 24. So starting at 0, subtracting 24, you get 24. That checks. And we know the slope of the moment diagram is equal to the shear. So what is the value of the shear at A? It is 0. So I should have a 0 slope. And the value gets bigger and bigger and bigger, and it becomes the largest here at B, and it's negative. So if I kind of sketch in a negative slope, I can kind of fit my parabolic shape like that. And there's my moment diagram. Okay, we've run out of time. So what I'll do is I'll finish this section here from B to C. It won't be on the video, but it'll be on this piece of paper, and you'll be able to access this through the notes section on the website. All right.